This you should already have in your review sheet, but it's basically the fact that current through any sort of conductor, like a wire, varies directly. So a direct proportion with voltage, but that your current is inversely proportional to your resistance. So as the resistance goes up, your current, or the flow of charges, goes down. So remember, resistors, just like the name, resist current, and they are inverses of each other. These proportions we came up with during our lab last class. So make sure you have both the definition and the, the equation and the definition coincide, but make sure you have that in your vocab sheet. There are also some parts to this equation that aren't intuitive. Obviously, V stands for voltage. I want you to also memorize that voltage can be represented, or another term I use to talk about voltage is potential difference. So you want to know that I interchange those two terms pretty frequently. So potential difference is part of your vocabulary as well. And then as we get into the different variables, there are certain ones that are harder to memorize, so you want to make sure to take the time to memorize those, which resistance is R, but the unit of measurement is ohm for omega. The potential difference is represented by V because that's also representative of voltage, which is measured in volts. That's pretty easy. If they could all be this easy, that would be nice. And then current is represented by I, and that is measured in amps, capital A. So basically, we have all these variables. We like to use nice variables to represent them, but we end up running out of those variables. So we start getting into the Greek letters. We start getting into just random leftover capital letters or lowercase letters that don't have any sort of correlation to the variable it's representing, but you just got to memorize. Any questions on the variables? If I say potential difference, what does that mean? Voltage, okay? So just because I don't say voltage, you have to know what that potential difference means, voltage. Resistors. I put this up because a student asked, what is a resistor made of? Well, first of all, we saw resistors like this in our last lab. Resistors can be the light bulbs or the appliances you plug into the electrical source. They can also be variable or fixed, but a student asked, what is it made out of? Well, here's my diagram. Carbon, it's got a carbon film, and then it's got a nichrome wire. The wires that are within those resistors are what allow you to determine the resistance. And I used the straw analogy with you guys last class, right? Okay, so you can think about, Josh, please. You can think about resistors like a straw. If you're in a competition where you want to drink a glass of milk as fast as possible, what type of straw are you going to choose? Well, when we're talking about resistance, sometimes you want to increase the resistance, which decreases the flow of charges. And to do that, you want a long wire and a thin wire, just like you want a long straw and a thin straw. So these are ways in which they construct those wires to make greater resistance. If they wanted less resistance, they make it wider and they make it shorter. There's other ways using temperature, as well as changing the type of material that the charge is traveling through, because we learned about how charges transfer much faster through conductors. And Wires are metal, but there are certain types of metal that transfer charges a lot better than others. Can I get you guys focused? Okay, these diagrams you've seen before. I want you to start memorizing them. A battery has a long and a short side. Sometimes you'll see them lined up as several batteries in a row. So this would mean you've got 3 batteries because you've got 3 positive and negative sides. You've got resistors, switches, and then a couple more would be your light bulb, your ammeter, and your voltmeter. So ammeter and voltmeter are at the bottom of your vocab sheet. It's pretty intuitive. They just measure amps or current, and they measure voltage. So if you want to include some of these symbols, you can do that in your vocab sheet as well. And I'm going to have these slides up on Canvas so you can look at them anytime you want to. Okay, let's get into series and parallel circuits. So your lab today is basically playing around with some models of circuits, and you can play around with them as much as you want, depending on the time constraint that I give you. But the 2 things I want you to really focus on is one series and one parallel. So here's my battery, here are my bulbs in series, and then if I had it in parallel, I would want to make sure I have individual loops connected to my battery. So this is what a series diagram looks like. This is what a parallel diagram looks like. Okay, so your circuits. Let me just switch my camera. Hi, physics students. So the activity that we did in class today, you can do through the simulation. I don't know why it's not closing for me, but basically we took a battery and we took some light bulbs and we set them up in series and we set them up in parallel. So if it's in series, you have one loop that is connected to 2 light bulbs and a battery. Now, if it's parallel, we're going to take the same voltage and we're going to take 2 light bulbs again, but we are going to connect them in their own separate loops to the battery. So I'm going to try to turn this around. And I'm going to add a little wire on each end. That's going to be helpful when we're calculating our voltage in and our voltage out. And then from there, I'm going to use a wire to connect it to the opposite sides of the bulb, as we learned from our light bulb activity. And you're going to make some observations. You're going to make some observations about the brightness of the parallel versus series, so those lights represent the brightness. And then you're going to make some comparisons in terms of the voltage and the current. So the current, this is a current meter. The current is the current through a wire, so you just touch it on the wire and it'll tell you how much current is flowing. You want to touch it in all different parts. So you want to touch it as it comes out of the battery and into the battery. You want to think about it as it flows from one wire into the bulb and out of the bulb, and same for the other bulb. So you're going to compare and contrast all these different currents, and as I'm showing you, you can notice the difference. You're going to do the same for a series circuit and notice the current in each of the different wires, how they change or don't change. And now when you're working with voltage,
A voltmeter has to be the voltage across a resistor, or in this case, our resistor is a light bulb. So you need a voltmeter on one side and the other side of your resistor to measure it. So this is the voltage through one light bulb, and this is the voltage through another. You can also test the voltage across a battery, which would be the total voltage of that battery, and this is a 9-volt battery. And same here. You would do the voltage of the battery because they're the same battery, it's 9 volts, and then you do the voltage across one resistor and the voltage across another resistor. So that would be the voltage of the wires on opposite sides of your light bulb. That's your resistor. So you're making some comparisons between the relationship of the current in a series versus the relationship of a current in a parallel, the relationship of the voltage in series and voltage in parallel, as well as the brightness. And then we're going to wrap it up into a conclusion. So make your observations. Our focus is just on series and parallel with 2 light bulbs each. This is your setup, so it's all set up for you. And then make sure you watch your video because I go into a lot of detail on the calculations and the patterns that are going to be important when you do your calculations for series and parallel circuits.
Okay. As we discovered, these are on, I know it's hard to see. This is the series. This is the parallel. So we're going to actually do some analysis with the current through them. First, let's start with voltage. So I feel like this is what parallel circuits look like with all the wires that are connecting them. So let's start with the voltage. Obviously, we've got 1.5 volt batteries. So these are going to be a voltage of 1.5 total, but we want to find the voltage through each light bulb, whether it's in series or in parallel. So the first thing I'm going to do is check the series circuit, and my voltage through series, I have to record this in order for you to see it, of a 1.5 battery gives me a voltage of 0.74 and a voltage of 0.73. So they're about the same. Oh, not that one working. 0.74 and 0.73. So I'm going to call this, where's my graph? .73 volts. Now, if I were to do it through parallel, the voltage through parallel is going to be 1.44 and 1.44. So notice the voltage through parallel versus the voltage through series. Much higher, much lower. Any thoughts why? Why would in parallel it would be much higher? Think about the loops. What do we know about the loops in parallel? What are each light bulb connected to that give it that high voltage? Come on, y'all. I know half the class is gone, but shouldn't be that hard. What provides the voltage? The battery, and they're both directly connected to the battery. So it's not exact, but I started off with a 1.5 volt battery, and I ended up with a 1.44 and 1.44 voltage drop, or potential difference, through each resistor, or each light bulb. So this isn't perfect, but what we come up with is the fact that as long as the voltage is in parallel, the voltage through voltage 1 and through voltage 2 should be about the same. Theoretically, it is the same, But in this case, we've got some source of error, because this is a real life example. And we've got some resistance in those wires. But for parallel, voltage stays the same. Now here I got 0.73, 0.74. It's not exact, but it's about what compared to my original voltage. I have 1.5 and it ended up as 0.73 and 0.74. Any patterns you notice there? None at all? Point seven, 0.7. Shereen? It's about half, not perfect, right? If it was 0.75 and 0.75, it would be about half of your total voltage. So it splits. This is your equation for series. The voltage for series is equal to the sum of your two voltage drops. So V1 plus V2. Now, we're going to look at current. The current that I calculate from our device is way off. I don't know why. So we're going to use a simulation, because the simulation is always going to be perfect, even though it's not real life. So let me just turn these off because I don't want my battery to die. And actually, let's verify. We're going to verify the voltage. Oh, other thing, I want you to notice in the simulation, these lines represent brightness. Look at how dim and how bright the parallel is versus the series. We're going to look at the current. So the current, when I go out of the battery, is 0.45. This is my series circuit. If I go through light bulb 1, 0.45, and through light bulb 2, 0.45. So the thing about series is that even though the voltage changes, the current, I, stays the same. Now let's look at the current for parallel. So the total current coming out of the battery is 1.8. But if I'm looking at the current that goes through light bulb 1, I get 0.9. And then if I look at the current that goes through light bulb 2, I get 0.9. So what do you notice about the current here? If I had a total current of 1.8 amps and each individual current was 0.9 amps, any pattern you notice with this one? Come on, people, it's the same. What's my pattern with a current when I have a parallel circuit? It's half. It splits. So my total current this time is equal to the sum of the current in each branch, in each part of the circuit that it splits up into. It's not always going to be half, but it's definitely going to add up to the total current for parallel, and the voltage is going to add up to the total voltage in series. So with resistance, it's a little bit harder. I'm going to give you those equations in a second, but in series, the resistance is just the sum of all the resistors. If I add two resistors in series, it's going to create more resistance. The odd thing is that if I had resistors in parallel, you're not adding the resistance of each one, but you're adding up the inverse of each resistance and then taking the inverse of that total. Weird. But we're going to do some calculation with it. What actually ends up happening is that by adding resistors in parallel, you actually decrease the total resistance so that it's even smaller than each of the individual resistors combined. So let's go ahead and go back over our series and parallel circuit items. So why is my mouse not working? Oh, let me switch this over.
So you want to make sure to write those points here that I included as part of series and parallel in your sheet. They're also in your physics helper. Okay, now music. Let's get into our slideshow. First of all, we already talked about series being a loop. Now we know that the current remains the same. And it basically means that your flow of charges, which is what current is, only has one wire to travel through. So because it only has one wire, then the current's always going to stay constant. And the resistors, if you add them together, is going to decrease the total resistance. Or sorry, it increases the resistance and it decreases the current because they're inverses of each other. Now for a circuit like this, as I stated, the resistor total just adds up. And if you look at the ammeter, which was the image I showed you, it's always going to stay the same, which is 0.45 for this scenario. But in a parallel circuit, all the components are directly connected to the battery in their own individual loops. So the voltage that travels through each resistor is constant. That's this equation. That it stays the same all the way throughout each parallel circuit. Now, here, the current changes. And the reason why is because now the current has multiple paths that it can travel through. It has total current here, but then it splits. And then once it reaches this part, it splits again. When they come back together, though, whatever current came out of the battery, as it goes and splits between each of the wires, it's going to come back together and be equal as it comes into the battery. So you can think about it like a river, or you can think about it like a set of pipes. If your pipe breaks off into two different streams, then the amount of water that flows through has to split as well. And that's how charges work when you have different wires in parallel. So the resistance, as I stated, is not easy to calculate. It's not hard to calculate. It's just more complex than simple addition. But the voltage stays the same because guess what? Each of those resistors are directly connected to the battery. So all of this we've gone over, but what are the advantages and disadvantages? The most obvious one is in series, and many of you stated this, if one light bulb goes out, the whole circuit is done. You can't work any part of the circuit if it has a break in its loop. So with parallel, you don't have that disadvantage because if one part of the circuit breaks, the other parts of the circuit still connect to the battery. And so there's no disruption in the energy or the flow of charges through this bulb, which is nice when you have one thing stop working, the rest of the things still continue to work. So there are certain things that are good to connect in series. Lamp dimmers are important to be directly connected to your light. Switches need to be directly connected to your light and your light source. Safety devices protect your home. So if one thing gets too overheated, everything shuts down. But obviously car headlights, if one headlight goes out, you don't want everything to go out. So these are connected in parallel. Most houses, if one light bulb goes out, you don't want your entire house to black out. So you can just replace that bulb and things will be fine. And then, in fact, they make newer holiday lights in parallel circuit as well. Because the way it used to be is that one light bulb in your Christmas light would go out and the whole thing would be done and you couldn't figure out where that broken light bulb was, so then you'd have to toss it. Now, the problem with parallel circuits, and I don't know what technology they use for holiday lights, but you don't want a ton of wires sticking out everywhere. If you have a parallel circuit and more than 2 light bulbs, 3, 4, 5, you're going to have tons of wires everywhere, and it becomes a tangled mess, which is not practical. So we don't use parallel circuits all the time. We already discovered that series is dim, parallel is bright. They're all connected directly to the battery, so they have more voltage. And for current, you can think about your toll booth as your resistor and your cars as the flow of charges. One resistor, not so bad. But resistors in series, if you had to go through 3 toll booths, one after another, you would hate your life, right? And then the way they actually set toll booths are in parallel, because this is even better than this, which is why I'm saying if you have resistors in parallel, it actually reduces the total resistance as opposed to just having one resistor, because now all these cars have multiple paths to travel through rather than just one. But obviously this is better than this, right? So we're not going to get into this today. We're going to start it next week, but there are different ways of doing problem solving for circuits. The cover-up method is the best method, something that I highly recommend because you're going to be interchangeably solving for voltage, resistance, and current. To set up a vertical circuit, I find this the most effective method just because if you think about a battery and a voltage drop can be viewed as a physical drop, like gravitational energy drops. So for series, your voltage drop through one resistor will add up to the voltage drop to your second resistor, and both of those together equal your total. The current, though, it's obvious that the current stays the same because it's going straight down through the same wire. Here, you have a voltage drop of R1 and R2, and those two are equal. In fact, they're the same as the total voltage that your battery started off as. So because they're parallel and vertical, you can see that the drop is the same. So V1 and V2 are equal to the total drop. The current, though, let me draw this out. The current, it's pretty easy to see that whatever current you start off with has to split up into 2 parts. So current 1, let's make this current 2. Current 1 and current 2. And that's what travels through each until you get to your total current, which is current 1 plus current 2. So that goes back to this equation right here. I'm not going to make you do this worksheet today. I want to go through more problem-solving strategies with you next class. So we've got our vertical circuit, we've got our cover-up method, and then I'm going to talk about the VIR chart that will be helpful for your concept builders. So I dropped the concept builders. It might say on Canvas that it's due, but it's not due. Just work on worksheet 2. And then you've got some chapters to read on chapter 35. And I want you to do more reading worksheets, 35-1 and 35-2. Other than that, start thinking about your project. We're going to have a series in a parallel circuit in your electric house. Save a box. It has to be shoebox size. You can add more to it if you want to make it bigger.
And we don't have enough materials for everyone to do it individually. So you have to find a group, either 2 or 3 people in your group, not 1 and no more than 3, okay? So start thinking about who you want to work with. Can't find a partner, I'll pair you up with someone. And then we'll have 1 workday class. No final for this class, but you're gonna have 2 mini tests on electricity and on magnetism. So I dropped the final. Your focus is basically trying to study for those mini tests and then your project. You might need more time outside of class. So if you have a friend that you can organize time with, that'd be nice. But if you don't, then don't worry about it. You can find time during tutorial or something to work on these as well.